In episode 29, titled Segmentation Fundamentals, Why Segmentation Fails and How to Make It Stick, we treat segmentation as a way to limit blast radius while preserving needed access, because the goal is not to block traffic for its own sake, but to make compromise and mistakes less catastrophic. The exam often presents segmentation as an obvious good. Yet in real environments, segmentation fails repeatedly because it is implemented without a sustainable model of what must talk to what. If segmentation is too strict without understanding dependencies, outages follow, and teams respond by adding emergency exceptions that never get removed. If segmentation is too loose, it becomes theater, because the network looks segmented on a diagram but behaves like a flat environment in practice. Making segmentation stick requires clarity about requirements, ownership, enforcement points, and the operational process that controls exceptions. The goal of this episode is to give you an exam-ready mental model for why segmentation collapses and a practical method to build it so it survives pressure. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Segmentation commonly fails when requirements are unclear and exceptions pile up, because ambiguity forces people to guess, and guessing creates outages that trigger permissive workarounds. If no one can state the business outcomes and the required flows, teams will implement broad allow rules temporarily to keep services running, and those temporary rules often become permanent. Over time, the rule set becomes a junk drawer, where every incident adds another exception, and no one dares to remove old entries because they do not understand what depends on them. The result is a segmented architecture that looks complex but provides little protection because the most sensitive boundaries have been perforated by accumulated allowances. In exam scenarios, you may see this described as too many firewall exceptions or segmentation is in place but lateral movement still occurs, which are cues that requirements and rule hygiene failed. The fix is not to add yet another control. It is to restore clarity by defining what access is truly required and by removing broad, unowned exceptions. Sustainable segmentation begins with requirements expressed as allowed flows, not as a list of blocked ports. Segmentation also fails when identity and ownership are not defined, because enforcement rules need stable identities to match and responsible owners to approve and maintain them. Identity can mean users, devices, workloads, or services. But the key is that you need a reliable way to refer to who is making the request and who should receive it in policy. Ownership means there is a team or role accountable for the segment's assets and for the rules that govern them, including changes when applications evolve. Without ownership, rules become stale, exceptions are added without review, and troubleshooting turns into finger-pointing during incidents. Without defined identities, segmentation rules become tied to brittle details like fixed addresses that change, leading to drift and unintended exposure. In exam terms, scenarios that mention unknown service owners or policies break during deployments often reflect identity and ownership gaps rather than purely technical firewall failures. A durable design ties segmentation to stable identities and governance, so changes are reviewed and rules remain meaningful. When you see unstable ownership, you should be skeptical of overly complex segmentation proposals because they will not be maintained. A strong starting point is to build an asset inventory and a flow map before writing rules, because you cannot control what you cannot name, and you cannot constrain flows you do not understand. An asset inventory identifies what systems exist, what they do, who owns them, and what data they handle, which is essential for grouping and prioritizing. A flow map identifies the communication dependencies, including north-south entry points, east-west service calls, and shared services like name resolution and time synchronization. Without a flow map, segmentation becomes a guessing game that either breaks critical dependencies or leaves broad openings because the safest guess is to allow too much. Flow mapping also helps prioritize because you can focus first on separating high-risk paths, such as user devices from servers and servers from management systems. In exam scenarios, the best answers often reflect this sequence by emphasizing discovery, mapping, and then enforcement rather than jumping straight to a complicated rule set. The key is that segmentation is an architecture practice, not a one-time firewall change, and it begins with visibility into assets and flows. Grouping assets by function, sensitivity, and change rate is a practical way to create segments that remain meaningful as the environment evolves, because these properties define how assets should be protected and how frequently their dependencies change. Function grouping separates workloads like user endpoints, application servers, databases, and infrastructure services because different functions have different exposure needs and different risk profiles. Sensitivity grouping separates assets that handle regulated data, secrets, or critical business processes from those that handle less sensitive workloads because the cost of compromise is not equal across systems. Change rate grouping separates stable infrastructure from frequently deployed application components because fast-changing components need policies that can adapt without constant manual updates. These groupings help you avoid creating segments that are too granular to manage while still providing meaningful containment. In exam reasoning, when a scenario mentions sensitive data, compliance, or frequent deployment cycles, grouping by sensitivity and change rate often points you toward designs that use stable identities and avoid brittle static allow lists. The best segmentation designs are those whose grouping logic remains valid when the environment changes, because that is what makes segmentation stick. Once you know what you are segmenting, choose enforcement points such as switch access control lists, firewalls, or host policies, because enforcement location determines both effectiveness and operational feasibility. Switch access control lists can be effective for controlling traffic within a local network segment or between local segments, but they can become complex and hard to audit when policies grow. Firewalls provide centralized enforcement and visibility at zone boundaries, which can simplify management, but they can become bottlenecks or single points of failure if all traffic must traverse them. Host policies and workload-level controls can enforce segmentation close to the workload, which aligns well with dynamic environments, but they require consistent management and monitoring across many endpoints. Often, the best design combines enforcement points, using centralized boundaries for north-south control, and local or host-based controls for east-west containment. In exam scenarios, enforcement choice is often constrained by operational skill level, performance needs, and where the traffic actually crosses boundaries, which is why the best answer tends to place enforcement at natural control points rather than forcing all flows through one choke point. The key is that enforcement must be aligned with the flow map, or else segmentation becomes either porous or disruptive. A common segmentation pattern is separating user devices from servers and from the management plane, because these three groups have distinct trust profiles and compromise risks. User devices are exposed to phishing, browsing risk, and frequent software variation, so they are often the most likely initial compromise point. Servers provide services and often hold sensitive data, so they should not be reachable broadly from user networks beyond what is required for business functions. The management plane includes administrative interfaces, control systems, and monitoring infrastructure, and it should be the most restricted because compromise there often means total environment compromise. Segmentation between these groups reduces blast radius because a compromised user device cannot freely access server networks, and a compromised server cannot freely access management interfaces. This pattern also simplifies logging and policy reasoning because flows between these groups should be limited and explicitly justified. In exam questions, when the prompt mentions lateral movement, privileged access, or internal compromise risk, this three-way separation is often part of the intended solution. The key is that segmentation is about creating meaningful boundaries that reflect risk gradients, not about creating countless tiny subnets. Segmentation becomes sustainable only when it is supported by an operational process with approvals, testing, and rollback, because the network is a production system and changes can cause outages. Approvals ensure that new access requests are tied to a real business requirement and have an accountable owner, reducing the chance of random exceptions. Testing ensures that new rules do not break critical dependencies, which is especially important when segmentation rules are tightened rather than loosened. Rollback ensures that if something unexpected breaks, you can revert quickly without improvisation, which reduces downtime and reduces the pressure to permanently loosen policies out of fear. This process is what prevents segmentation from degrading into emergency rule changes that accumulate forever. It also creates an audit trail, which can be important in regulated environments and helps identify when a temporary exception should expire. In exam reasoning, answers that include change control and rollback often aligned with best answer logic because they recognize that segmentation is not only a security design, it is an operational discipline. The key is that a good rule is one you can maintain safely, not just one you can write once. Shared services like domain name system complicate segmentation designs because many systems depend on them, and blocking them can break everything in ways that feel unrelated. If you segment without accounting for shared services, you might successfully block unwanted flows, but also block name resolution, time synchronization, authentication, or logging paths that are required for normal operations. This often triggers emergency exceptions that are overly broad because teams under pressure allow wide access to fix DNS, and those broad allowances can undermine segmentation intent. The better approach is to treat shared services as explicit dependencies in the flow map and to provide controlled access paths to them from each segment. This might involve dedicated infrastructure zones, carefully scoped rules, and strong monitoring for those service dependencies. In exam scenarios, if you see segmentation implemented and then everything fails, shared services are often the hidden cause because they are common dependencies that were not included in the initial plan. The best answer typically recognizes shared services as first-class flows that must be permitted in a controlled way rather than ignored or handled with blanket rules. The lesson is that segmentation must preserve the lifelines that allow the environment to function. Another pitfall is overly broad rules that negate segmentation and hide problems, because broad allowances create a false sense of safety and reduce the ability to detect abnormal behavior. If a rule allows entire subnets to talk to each other on all ports for convenience, then segmentation boundaries become meaningless and lateral movement becomes easy. Broad rules also hide dependency issues because everything works, but you no longer know what should work. So misconfigurations and suspicious flows blend into the background. During incidents, broad rules slow investigation because you cannot narrow the possible paths, and you cannot rely on policy to have constrained the attacker's movement. In exam scenarios, the presence of allow any style rules is often implied by phrases like flat internal network or no east-west restrictions, and the correct answer typically involves tightening rules to least privilege. The challenge is to tighten without breaking operations, which is why flow mapping and incremental change are critical. The best segmentation does not block everything. It allows only what is needed, and broad rules are the opposite of that discipline. A practical way to make segmentation stick is to baseline traffic and then tighten incrementally with metrics, because sudden strict enforcement often causes outages and triggers rollback to permissive defaults. Baselining means you observe what flows actually occur today, identify which ones are necessary, and identify which ones are unexpected or risky. Tightening incrementally means you restrict one boundary at a time, verify impact, and then proceed, using measurable success criteria such as reduced lateral reachability without increased incident volume. Metrics matter because they provide evidence that segmentation is improving security without harming reliability, and they help you detect when a new rule causes hidden damage. Incremental tightening also builds trust with stakeholders because it demonstrates that segmentation is being done responsibly rather than as a disruptive security mandate. In exam terms, answers that emphasize gradual tightening and validation often align with practical best practice, especially when the scenario implies limited tolerance for outages. The key is to treat segmentation as a program, not a switch, and to use data to guide each step. A memory anchor that captures the sustainable approach is inventory, flows, groups, enforce, then iterate safely, because it preserves the order that prevents most segmentation failures. Inventory ensures you know what exists and who owns it, because unknown assets and unknown owners create drift and blind spots. Flows ensure you understand dependencies, because segmentation without dependency knowledge produces outages and broad exceptions. Groups ensure your segments are meaningful, based on function, sensitivity, and change rate, which makes policies durable. Enforce ensures you place controls at appropriate points, such as firewalls, access control lists, or host policies, aligned with where flows cross boundaries. Iterate safely ensures you use approvals, testing, rollback, and metrics to tighten over time without destabilizing production. This anchor is useful for exam questions because it reveals when an answer choice skips steps, such as proposing strict enforcement without any flow understanding. When you can recite this anchor, you can justify why a disciplined approach is best. To end the core, design 2 segments and the required allowed flows, because this exercise matches how you should think in scenario questions. Imagine one segment is user devices and the other segment is application servers, and you must decide what should be allowed between them. User devices should be allowed to reach specific application entry points on specific ports, but they should not have broad access to back-end services or administrative interfaces. Application servers may need to reach shared infrastructure services such as domain name system and time synchronization, and they may need to reach a database segment, but those flows should be explicit and limited to required ports. Management access should not be broadly allowed from the user segment, and management paths should be constrained through controlled gateways and strong identity checks. You also account for monitoring flows because logs and telemetry must cross segments to support operations and security investigation. The point is that segmentation success is measured by a small set of clearly justified allowed flows, not by blocking everything or allowing everything. When you can describe these flows cleanly, you can answer exam questions about segmentation with confidence. In the conclusion of episode 29, titled Segmentation Fundamentals, Why Segmentation Fails and How to Make It Stick, the main failure causes are unclear requirements that produce exception sprawl and missing identity and ownership that make policies brittle and unmaintained. You start with an asset inventory and flow map, group assets by function, sensitivity, and change rate, and then choose enforcement points that align with where traffic crosses boundaries. You recognize that operational process matters, using approvals, testing, and rollback to avoid outages that trigger permanent permissive exceptions. You account for shared services like domain name system as explicit dependencies, and you avoid overly broad rules that negate segmentation and hide abnormal behavior. You build quick wins by baselining current traffic and tightening incrementally with metrics, so segmentation improves security without destabilizing production. Assign yourself one segmentation plan narration by choosing a small slice of an environment and stating the inventory, the key flows, the grouping logic, the enforcement points, and the incremental tightening plan aloud, because that narration is the disciplined thought process the exam expects you to apply. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.